Welcome to another video in the Sunrise series showcasing the outcomes of Use Case 2 Traffic Jam Ad Validation 2.1 Safety Assessment and Decisions-Making Testing. In this video, we test a traffic jam chauffeur. We assess how the system behaves in different traffic jam conditions. 5 parts of the SAF will be demonstrated, namely query and concretize, allocate, execute, test, evaluate, and decide. The CCAM system under test in an cooperative advanced ACC. The scenario demonstrated in this figure is a cut-in scenario on a highway. The test case setups are based on simulation, proving ground, and public road testing. We followed a safety argumentation checklist that covered a microscopic evaluation of results for individual scenarios and safety case pass-fail binary results. Key artifacts include querying, concretizing, allocating, executing, and test evaluating. The querying process within this block of the SAF was performed using individual scenario databases as the established link from the Sunrise data framework was not yet operational. Safety Pool database is used as a source for some of the scenarios within this use case. In this video, we demonstrate a scenario search query within the Safety Pool UI, which uses open label tags to enable scenario query. The scenarios for Sunrise are contained within a demonstration library. This library is queried for appropriate tags. The tags for the search come from the ODD attributes and behaviors contained within the use case definition. The search is specific to the use case and retrieves the 11 logical scenarios which were intended for this use case, out of a wider selection of scenarios within the library. The logical scenarios can then be downloaded in OpenScenario and OpenDrive formats for concretization and simulation via the local UI, or added to a test suite for API retrieval. Same as for Safety Pool, although an API is in place for the querying, the Streetwise GUI was used as the established link from the Sunrise data framework was not yet operational. The first step is to translate the logical scenarios defined in this use case to scenario categories available within the Streetwise database, including the appropriated tags. Since the Streetwise database does not store the actual scenario, but uses a parameterized approach, the parameter distribution for the scenario categories can be visualized. The second step would be to select the desired ranges for the parameters that make up the scenario, which also always for a coverage computation. Finally, a Monte Carlo approach is used to generate the actual concrete scenarios, which are in this case outputted in OpenScenario and OpenDrive files. AVL Scenius provides an end-to-end solution for scenario generation from various sources, built on a flexible and efficient database structure. Also, Scenius allows for rapid querying, concretizing, and dynamic test case creation. In this workflow, target cut-in scenario is selected, and a wide range of test cases is automatically generated based on parameter ranges. In Step 1, Scenario Artifact in OpenScenario format is uploaded to AVL Scenius Scenario database together with the environment file in OpenDrive format. Then in Step 2, AVL Scenius Scenario database extracts the parameters in the scenario file and allow user to create variations. User can specify min-max values and step sizes for each scenario parameter. The user can also specify concrete parameters. After configuring the parameter space, the user can generate concrete test cases with numerous methods like full factorial, combinatorial, and active DOE. This time full factorial is selected. In the last step, finally, the user can view and download the generated concrete test cases in OpenScenario file format. After this step, these concrete test cases can be directly executed through the user interface. These test cases can be further refined through a user-friendly interface. Once ready, execution is triggered directly from AVL Scenius, and all concrete scenarios are seamlessly transferred to AVL Scenario Simulator for simulation. In this phase of SAF validation, the goal is to assign each test case to the appropriate testing environment. This allocation is based on operational design domain criteria, mainly vehicle speeds and accelerations. According to the process defined in document D3.3, it is expected that all test cases for decision logic evaluation will be initially allocated to simulation. However, tests with a strong focus on validation, as identified by domain experts, will be allocated to proving grounds or public road testing. A key point here, test cases will not be reallocated. The priority in this demonstration lies in validating the framework itself, not in guaranteeing the safety of the system under test. On the right side of the slide, you see a table of use cases, each with an illustration and description. The final columns show where each test will be validated, either in proving grounds, on public roads, or through simulation. This structured allocation process ensures efficiency, traceability, and safety throughout the validation workflow. After test cases have been allocated to the appropriate environments, it's time to run them. This execution phase is essential for verifying how the system under test behaves in real conditions, whether virtual or physical. We use 3 key environments for execution. First, simulation. It offers a safe, repeatable, and cost-efficient way to test edge cases and complex scenarios. Here, we see the system identifying vehicles, lane markings, and reacting accordingly, all within a controlled virtual space. Next is the proving ground. This test track allows for high-precision testing with real vehicles, but without the unpredictability of public traffic. Real-world sensor data is collected under reproducible conditions, enhancing system reliability. Finally, we have public road testing. This is where the system is exposed to the complexity and variability of real-world driving. It's the ultimate check to ensure that the system performs safely in everyday conditions, while interacting with unpredictable road users and infrastructure. Together, these environments ensure robust validation from simulation to real world. The simulation focuses on lane centering and distance-keeping functions. At its core is the AVL Scenario Simulator, a co-simulation platform that synchronizes multiple tools to create a unified test environment for ADAS evaluation. The toolchain includes 4 key modules. Carla, for realistic 3D scenes and sensor simulations essential for ADAS visualization. Esmani, for scenario playback using open scenario files to test system behavior across varied situations. AVL VSM, to model vehicle dynamics and validate control responses. ROS, both as the control algorithm platform, for lane centering and adaptive cruise control, and as the integration interface managing data exchange. With AVL Scenario Simulator coordinating these tools, the setup provides a modular and realistic simulation environment for developing and testing ADAS controllers before real-world deployment. For the evaluation of the target cut-in scenario, the KPIs outlined the UNR 157 regulation are used. Each KPI has thresholds and a pass-fail status determined. After the simulations are completed, the result of every KPI is calculated then displayed on the UI. The KPIs and their respective thresholds are defined in AVL CNEUS Acceptance Criteria page. The list of KPIs are minimum time to collision, minimum headway distance, comfortable and maximum longitudinal/lateral accelerations, longitudinal jerk and collision occurrence, and they are defined alongside their UNR 157 thresholds. The example shown met all UNR 157 limits and recorded as pass, green color. With respect to this approach, rest of all scenarios are evaluated for pass-fail criteria. In this slide, we focus on executing test scenarios in the proving ground, a controlled environment that enables high-fidelity testing of complex traffic situations. At the center of this setup is the Vehicle Under Test, or VUT, which is equipped with DGNSS and IMU sensors and connected via a Wi-Fi mesh network. It interacts with a base vehicle, which coordinates the test execution and controls the testing platform. On the other side, we have the platform system, also connected through Wi-Fi and equipped with precise positioning. It manages movable elements like pedestrian or car dummies. This setup allows for repeatable and safe execution of critical scenarios, including pedestrian crossings, cut-in and cut-out maneuvers, and blocked lane situations. Thanks to the high precision and controlled conditions, the proving ground provides crucial insights into system behavior under near-real conditions, without the unpredictability of public traffic. This ensures safe and systematic validation of decision logic and perception systems. In this video, there can be seen a pedestrian crossing, a cutout, and a cut-in scenario executed on the proving ground. In the bottom left corner, there can be seen the instrument cluster of the vehicle under test. In this phase of the SAF block validation, the focus is on real-world execution, conducted on public roads. The vehicle under test, VUT, operates in live traffic, interacting with real vehicles, pedestrians, and infrastructure. This slide shows the setup used for black box testing of an SAE Level 3 production vehicle on German highways. The setup includes data logging, GPS and Wi-Fi antennas, and IMUs to monitor the vehicle behavior. A secondary target vehicle was also equipped to stage realistic scenarios and interactions. The system architecture enables synchronized communication between those two vehicles via differential GNSS, Ethernet, and Wi-Fi, ensuring reliable data exchange throughout each test drive. By validating in real traffic, we can evaluate the actual performance of the system under test and verify that it operates safely and predictably under the dynamic and often unpredictable conditions of real-world driving. In the video on this slide, a four-way split screen is shown, featuring footage from two different test drives on public roads during a cut-in scenario. In both scenarios, an SAE Level 3 system is active, with the driving task fully managed by the system. In the first video, a vehicle overtakes the test vehicle and cuts in ahead of it. The ego vehicle system responds by decelerating and adjusting its speed to the traffic situation. The second video shows a similar scenario with a cut-in from the right side. Additionally, the perceived vehicles are visible in the instrument cluster display. This slide shows the validation process for the SAF block, focusing on the test evaluate step. Key metrics include longitudinal acceleration, relative vehicle distances, time to collision, TTC, and whether a collision occurred. KPIs are based on UN Regulation Number 157, covering limits for acceleration, jerk, TTC, and system reaction time. The data plot on the right illustrates a cut-in scenario from proving ground tests, showing how speed, acceleration, and relative distance evolve over time. We can see that the system avoided the collision by adapting its speed to the target vehicle's speed. Below that, the table provides required time gaps and following distances for ALKS systems depending on vehicle speed. Here, all previously generated outputs are brought together to support a final safety argument decision. This includes results from the test evaluate, the safety case, and, although not demonstrated in this use case, coverage. After reviewing all sources, although the coverage was not evaluated in this use case, the system was assessed and has been considered as safe. For formal auditing, for example, from the perspective of a type approval authority, the Sunrise Interactive Handbook provides application guidelines that can be followed. In this video, we have shown the Sunrise SAF has proven effective in providing valuable guidance for ADS safety validation, demonstrating scalability and versatility through black box testing of an SAE Level 3 system with a state-of-the-art vehicle. Robust test setups across simulation, proving ground, and public road environments ensured reliable and repeatable validation results. Future work includes conducting coverage analysis and reallocation, as well as further integration of simulation and physical testing systems.